Greetings and welcome to my first try at recording one of these suckers. It won't be perfect, but hopefully it'll be useful. So, hypothesis testing with two samples, Chapter 8. All of these that we're going to be talking about here, all of these hypotheses samples, it can be thought of as the difference of means tests. So we're looking at the mean of one group compared to the mean of another. We're not looking to see whether a mean of a sample is different from the total population mean. That's what we did in the last chapter. This is where we're actually going to be comparing two sample means to each other. Now, the first ones that we're going to be covering, because they're a little easier, are when we have what are called related samples or dependent sampling, where basically in these cases, in these two samples, these two groups we're comparing, they're related to each other in some way. One common way that this happens is in what's called within subjects research. Now, you'll run into this again when you do research methods, but within subject research is when we use the same subjects as both the experimental group and the control group. Where the group, for instance, if you're testing a medication, this group will both be tested or be given a depression test, for instance, with the medication and a depression test without the medication. And then they'll compare the two means. So we're using the subjects as their own controls. This runs into problems which you'll learn more about in terms of variables we can't control for all of them. Time could be a problem here. Maturation, development could all be a problem. But hey, sometimes it's what we have to do. Other times is when we have what are called matched groups. This is, for instance, if you want to make sure that in your group you have the same number of people who do really well in school, for instance, if you're doing something about education, and the same number of people that maybe don't do as well. Now, random sampling for the two groups should give you that, but sometimes you want to be sure that group A and group B both have the same percentage of various people getting various grades. And so what they'll often do then is, instead of truly random sampling, they'll make sure, well, this person has an IQ of, 120, and so we need to match them with someone else who also has an IQ of 120. They're related to each other. Sometimes researchers will then basically ask, say, members of a family or the two individuals in a couple, or the three in the throuple, however we want to run it, or friends, or so that, again, they're not selected independently. You're selecting them because of subjects you already have. And so what we're trying to do here to determine whether or not the difference between these two means is significant, we're looking at how extreme our observed differences between the two means. And then we're going to compare that to all the possible differences that we might observe. We're back to talking about what we talked about in prior chapters. We're back to talking about the central limit theorem and the fact that all of these samples that we could pull, the means of the various samples will probably all be different. So we're looking to see how unlikely it is that these two sample means that we have are the same or are different. So, compared to all the possible examples that we could have. Since we're not doing a census, since we are picking samples and not selecting everybody, then the means will depend on the particular sample that you pick. And so what we're doing here then is saying how likely it is, compared to all the possible samples that we could pick, all the possible means we could compare, how likely is it that these two, there's no difference between this group and this group. Again, it's related to what we've been doing. So, here again we're going to do a t-test. Remember the difference between the t-test and the z-test. Take a second to try to think of it. In the z-test, we know the population standard deviation, the population variance. In the t-test, we do not. And we're assuming at this point that we do not. So I'm going to start throwing equations at you. But again, the nice thing about these equations that I'll be hurling in your general direction is that they're all pretty similar to what we've already covered. Here we go. The first step, and I will give you the traditional step-by-step process in just a second. But to perform a two-sample hypothesis test with dependent samples, First, we need to look at the difference between each pair. Okay, we've got matched samples, we've got couples, we've got the same person, both before and after. So little d is basically the difference between the first score and the second score, whether it's for the same person or for a matched pair or for a couple or for whatever. It's the difference between the entries. That's little d. Now, the test statistic, one of the important things that we're going to be looking at is essentially the mean, the average of these differences. This should be sounding familiar, shouldn't it? It should be sounding a little bit like, oh, when we started talking about stuff like sum of squares, except in this case, we don't have to square them. Okay, where you got the difference and then you squared them because otherwise they would all add up to 0. Well, the thing is, these are not going to all add up to 0. So all we have to do for big D bar, big D, I usually say X bar, so this is big D bar, is equivalent to all of the differences for your entire sample. So all of those individuals, both before and after, all of those couples, all of those matched pairs, you take all of those differences, you sum them up, and you divide them by n, the number of sample pairs that you have. So we're basically taking the average of the differences here, the mean of the differences between them. Notice that it's not necessarily n here is, remember, not exactly, it's the number of subjects. It's the number of data entries. Okay. So we've got d bar equals the sum of d's over n. With that, we can find the standard deviation. The standard deviation pretty much is what it sort of looks like. I apologize, that square root should be covering everything, but PowerPoint is not letting me do that. So assume when you write it that the square root is covering everything. So the standard deviation of d is equivalent to the sum of each particular difference minus the mean of the differences squared over n minus 1. Okay, so you find all the d's, you find the mean of all the d's, that's big D bar, you subtract big D bar from the little d, each of them, get that difference, square it, divided by n minus 1, that gives us the standard deviation of these differences. That's what the d is, the standard deviation of the differences. So now that we've got some numbers and we've got some equations, we got to go, okay, what's the null hypothesis? The null hypothesis here, well, think about it for a second. What would the null be? The null hypothesis is that there's no mean difference between the two groups. That basically two groups are going to give us, if we could do the entire population and such, that we're going to get the same. Okay? And this is when we start bringing forward the good old central limit theorem. Ta-da! Central limit theorem. Since the mean difference is 0, according to the central limit theorem, the mean of the sampling distribution of mean differences is also 0. Remember before we had sampling distribution of the mean of the samples being 0? Well, samples, differences, same thing. Central limit theorem. So therefore, because we can go with the central limit theorem, because we know that our null hypothesis would say that the difference is 0 and the central limit theorem says, okay, so therefore the mean of the sampling distribution of mean differences is also 0, we need to find the standard error of the mean differences. Remember back when we were talking about doing the t-test before, we also had to use the standard error and not the standard deviation, because we didn't know what the standard deviation was. So what do we have here? We have the standard error of the mean differences, which is S sub big D bar. it's easier to just look at it. It's equivalent to that standard deviation of the differences there, divided by the square root of n. And as I mentioned before, this should be looking really familiar. It really should. Because it's essentially the same principles that we've been covering for the past month or so. It's just that we're doing it for slightly different examples, and we're doing it looks a little differently. We're using different letters, but essentially it's the same thing. It's part of the reason why when people ask me if there's going to be information from prior chapters on the test, the answer is kind of yeah, because essentially what we have here, at least a little bit, is we have here stuff that's building on what we've learned before. Okay? It's building on what we've learned before. Now, given all of this I just gave you, given what you remember from the t-test from before, okay, for what we did in prior chapters, here's the complete formula for the calculation of the t-ratio with related or dependent samples. T-score is big D bar minus mu. Remember what's mu? Mu is the population, basically. It's the mean of the population of D bar, which, by the way, happens to be 0. More about that in a minute, because that's what we're assuming from the central limit theorem, right? That the mean of the differences is going to be 0 because the null hypothesis is there is no difference between those two. Okay? Divided by the standard deviation of big D bar, the standard error. Okay, standard error is actually what it is. Sorry, I used to get stuck on standard error. But since we're assuming, as I said before, that the mean of the difference between the two populations is 0, we can drop that, and there is the equation, which is a whole lot less scary. To find the t-score, we take big D bar, the differences between the mean of the sampling differences of the mean differences divided by the standard error. A lot simpler once you figure out, remember what all of those are. Once we got that done, we look up the critical value, given the level of significance, exact same thing that you did before with the t-test, 0.05, fantastic. Compare our t-score to that to see if we should reject or fail to reject. And remember, just like before, what we're going to be doing here is if our t-score is more extreme than that critical value, then we're going to reject the null. If it is not more extreme, if it is not larger than the critical value, then we are going to fail to reject the null. And with that, since I'm almost out of time, I'm going to pause here and start a new video where I'm going to give you a little bit more of a step-by-step and then give you an example. See you in a second. Well, hear me in a second.